Another common pattern besides the arithmetic, where we add each time to get to the next term, and the geometric, where we multiply by the same number each time to get to the next term, is a quadratic pattern, and it's called a common second difference, and I'll show you why that is. If we look at the pattern in the first sequence, we'll notice that first we add 3, then we add 5, then 7, then 9, and then 11 to get to the next term. So the next term would be 36 plus 13, which would be 49. And we could continue that pattern quite easily. But how do you find, say, the 100th term down the line without having to add all the other ones before that? Is there an explicit rule that we could use? So what I want you to notice is when we did plus 3, plus 5, plus 7, plus 9, plus 11, the second time we find the difference, it is a constant. So this is plus 2, plus 2, plus 2. In other words, the difference of the differences is constant. Whenever you see this pattern, when you're adding 2 each time, the second time you find the differences, it means that the rule has an n squared in it. So if n equals 1, 2, 3, 4, 5, 6, a sub n equals n squared. Now in this case, it's just a sub n equals n squared. You can see that these are all perfect squares. But what about one that has something slightly different? So let's look at the second one. This one, we see the same pattern where we're adding plus 3, plus 5, plus 7, plus 9, plus 11, and we have that constant second difference, plus 2, plus 2, plus 2, plus 2. So that means that there is an n squared in the rule. So I'm going to number the terms. So a sub n equals n squared. Now if we square n, I'm just going to write this above. N squared would be 1, 4, 9, 16, 25, and 36. And if you look at the actual terms, 3, 6, 11, 18, 27, and 38, you'll see that they're all 2 bigger than the square of the term number. So it's just n squared plus 2. Once again, fairly simple. Now we're going to get a little harder after this. So let's look at this third one. If we go through and find the second difference, okay, so we see this is plus 6, plus 8, plus 10, plus 12, plus 14. So we still see a common difference, plus 2, plus 2, plus 2, plus 2. So it has an n squared. So we know that a sub n equals n squared. It just means it's quadratic. It could be n squared plus something n plus something. So it gets a little more involved. So this one I want to, if we just square the terms here, so let's just, or square the term numbers, let's make a list here. I'm going to say n is my term number, so here are my n values. And I'm doing this because I already know this one's a little more complicated. 1, 2, 3, 4, 5, 6. So n squared would be 1, 4, 9, 16, 25, and 36. So when I look at these terms, the first 6 would be n squared plus 5. So n squared plus 5 equals 6. Oh, maybe it's just plus 5. Nope. Because for term number 2, it would be n squared plus 8, because it would take 4 plus 8 to get 12, and 9 plus 11 to get 20, and 16 plus 14 to get 30, and 25 plus 17 to get 42, and 36 plus 20 to get 56. So notice here, I'm having to add 1 plus 5, 4 plus 8, 9 plus 11. So it's n squared plus, okay, how do I get these numbers now? 5, 8, 11, 13, 17, 20. Notice, though, they're all going up by 3. Okay? So notice here, plus 3, plus 3, plus 3 plus 3. This is an arithmetic sequence. 5, 8, 11, 15, 14, 17, 20. And I know in an arithmetic sequence, if I add 3 each time, it's going to be 3 times n plus something. So I'm going to add now here plus 3n. Actually, I don't think I'm going to do that over here. I think I'm going to make another little table. So here's n, and then I'm going to do n squared plus 3n. Okay, so 1, 2, 3, 4, 5, 6. Now I want to go back and say, I know that it had an n squared because the second time I did the difference, there was a difference of 2. I know that it has a 3n in it because the first time I did the difference with these extra terms that I hadn't accounted for yet, it had a difference of 3, which means it's going to go up 3 each time. So it's going to be 3 times n plus something. So if I do n squared plus 3n, so put in 1 squared plus 3 times 1 would give me 1 plus 3, 4. Okay, then 2 squared plus 3 times 2 would give me 10, and 3 squared plus 3 times 3 would be 9 plus 9 is 18. 4 squared plus 3 times 4, 12 plus 16 is 28. 5 squared plus 3 times 5, 15 plus 25 is 40. And 6 squared plus 3 times 6 would be 36 plus 18. I can tell from the pattern now this is going to be 54. Because notice 4, 10, 18, 28, 40, 54, 6, 12, 20, 30, 42, 56, all of these numbers are 2 less than what I want them to be. So all I have to do is add plus 2, plus 2, plus 2, plus 2, plus 2, plus 2, and I get what I want, 6, 12, 20, 30, 42, 56. So here's my rule. A sub n is equal to n squared plus 3n plus 2. This is a really challenging one, so I'm just going to tell you that. This is challenging. However, sometimes on these really challenging ones, there is a shortcut, and I'll show you the shortcut to this one. It's kind of an interesting little shortcut. Let me just rewrite the sequence again. 6, 12, 20, 30, 42, 56. Well, I already know from my pattern that it's going to have an n squared in it. It's going to be quadratic. Well, quadratic things can factor, okay? In other words, it could factor to n plus something, or n minus something times n minus something. So anywhere, if I could figure out 2 numbers that multiply together that involve my term number n, then that would be another way, another alternative for finding the pattern here. So let's think of numbers that multiply together. So there's more than one way to multiply, but on each of these, but we want to find something that sort of has a pattern. And what I notice is, I could think of this as 1 plus 6. Would this be like 2 plus 7? No. Sorry, I'm not pointing. Like 6 is 1 plus 6, but then would this be 2 plus 7? 2 times 7? No. But what if I did 2 times 3 here? 2 times 3. 3 times 4. 4 times 5. Ooh, I've got it. 5 times 6. 6 times 7. 7 times 8. So what's the pattern? 2 is n plus 1. 3 is n plus 2. And that's the case here. 3 is n plus 1. 4 is n plus 2. 5 is n plus 1. Or sorry, 4 is n plus 1. 5 is n plus 2. So my rule is a sub n is equal to n plus 1 times n plus 2. Both of these are explicit rules because they only involve the term number. So if I wanted to find term number 100, it would be 101 times 102. That would be term number 100. If I multiplied this out, it would be n squared plus n plus 2n plus 2, or n squared plus 3n plus 2. So that's 2 different ways of finding the pattern for that particular quadratic. Now let me show you one more, and hopefully I have left enough room for it. This one's slightly different. When I add, this time it's plus 5, plus 9, plus 13, plus 17, plus 21. And you know what? I just realized something. On number 2 here. Oh, this is the one that's wrong. Okay, this is the one that's wrong. I believe. Or maybe did I correct it? 50, 71. Nope, this is the one that's wrong. Because if I add 13 to 20, I get 33. So this is actually supposed to be 33, 50, and 71. I messed up when I wrote the pattern. Okay. Anyway, we're supposed to see a constant second difference. However, in this case, our constant second difference is not 2, it's 4. What that tells me, instead of having an n squared in it, it has a 2n squared in it. That means that a sub n has to be 2n squared plus something plus something plus something n plus something. Now it could be plus 0n or plus 0, but anyway, it could be in this form. If there were 6, if this was the constant second difference was 6, then it would be 3n squared. If it's 5, I've never done one with 5. I would guess that it would be 2.5 n squared, but I'm not positive. I would guess that's what it was, like 5 halves n squared. So anyway, that has a 2n squared. So I'm going to start by playing around with the 2n squared. And I just figured this out this year. After doing these patterns for many years, I never quite figured out how to do the ones that had something other than 2 as a second difference. I never realized that that always meant it was 1n squared and that this was 2n squared. So that's a little helpful thing that now I can pass on to you. I figured that out just by playing with these. So if we number our terms, 1, 2, 3, 4, 5, 6, and we put in 2n squared, let's see what we have left. So we're trying to get the terms 6, 11, 20, 33, 50, and 71. So 2n squared would be 2. This would be 8. 2 times 3 squared would be 18. 2 times 4 squared, 16 times 2, 32. 50 times 2, I'm sorry, 25 times 2 is 50. 36 times 2 is 72. Ooh, this isn't too bad, maybe. Maybe not. Ooh, this is a little tricky. So now, in order to get to the term I want, on term number 1, I would have to add 4. So 2 plus 4 gives me 6. To get to term number 2, 8 plus 3 is 11. 18 plus 2 is 20. 32 plus 1 is 33. 50 plus 0 is 50. And 72 minus 1 is 71. So notice I have an arithmetic sequence that is going up by 1 each time now. So this is plus 1 each time. Plus 1. So that means it's going to be plus n. Okay, so 2n squared plus 1n. Okay. Now, if I add 1n to each one of these, and I think I'm just going to erase, so let me just make another column now, 2n squared plus n. Okay. I'll just leave that off now. This just shows me what else I needed to add. So 2n squared plus n would be 2 plus 1 is 3. 2 times 2 squared plus 2. Oh wow, this is getting complicated. 8 plus 2 is 10. 2 times 3 squared is 18. Plus 3 would be 21. 32 plus 4 would be 36. I forgot I'd already done the 2n squared here. 50 plus 5 would be 55. And 72 plus 6 would be 78. So now, how do I get to, this is weird. this isn't plus 1, this is minus 1. No wonder this isn't working. I'm silly. I'm not adding plus 1 each time on this previous row. I'm subtracting 1. Oh my gosh. Let me do this. Where's my eraser? Can't find my eraser. Okay, eraser. Let's erase here. All right. Back to the drawing board, as they say. So this is instead plus 1. It is minus 1, minus 1, minus 1, minus 1, minus 1, 1. Which means instead of adding, I'm subtracting here. This is minus n. Okay. I knew things weren't looking right when I did this. Okay, so 2n squared, which we already have. So 2n squared is already in this list. So now I'm just going to take 2n squared minus n. So 2 minus 1 is 1. 8 minus 2 is 6. 18 minus 3 is 15. 32 minus 4 is 26. 50 minus 5 is 45. And 72 minus 6 is 68. And then I would need to add 5 to get, that would be the last thing I'd need to do. So to get to 6, I would have to add 5. To get to 11, I'd have to add 5. To get to 20, I'd have to add 5. 26 to 33, something went wrong. Probably because I subtracted wrong. That was supposed to be 32 minus 4, which is 28. And 28 plus 5 is 33. 45 plus 5 is 50. And 68 plus 5, once again, I subtracted wrong. 72 minus 6 is not 68. You guys are probably screaming half point at me by now. 72 minus 6 is actually 66, and then you add plus 5 and you get 71. So my final rule is 2n squared minus n plus 5. 2n squared minus n plus 5. A sub n equals. And that means I could plug in, if I want to know the 100th term, I could plug in 100, figure out exactly what the 100th term is. You have to make sure your rule works for every one, and I just checked that it worked for all these terms, so that is my rule. This one, you couldn't do the nifty little multiplication trick, because if you tried factoring this to 2n and n, there aren't any nice numbers that would end up giving you 2n squared minus n plus 5. So it isn't one where you can find a nice multiplication pattern. That's really handy when you can, but you can't on this one. So this one I had to go through, find the squared term, and this one, this is the key, is knowing that the plus form means it's a 2n squared. Then find the arithmetic sequence that gave us the rest, which was basically negative n plus 5 or 5 minus n that I'd have to add on to here. So that's a quadratic pattern. And so when you encounter something that has a constant second difference, now hopefully you'll have some strategies for dealing with that.